So here's another example where we want to combine our exponent rules and use them all together. First off, we said we'd look for parentheses, places where we could multiply the exponents. Looks like we have parentheses and exponents to multiply on top here. So let's keep the base a, multiply the 3 and the 5 to make 15 using our power rule. And then we have something similar on the bottom. Let's keep the base a, multiply the exponents. 10 times 4 makes 40. And then it looks like we don't have any bases side by side that are being multiplied, so we don't need the product rule, but we can move along and use our quotient rule since these bases match and they're being divided. So quotient rule says keep the base and subtract the exponents. We want to take the top one minus the bottom one. So 15 minus 40 makes negative 25. And now there's nothing else to combine, but because of that negative exponent, we'd like to go one more step and use our new definition to turn this negative exponent into a fraction. 1 over the same base a raised to the positive 25th power. So that expression simplifies a good bit down to 1 over a to the 25th. This would be a great time to pause the video, try the 4 examples down below, using the exponent rules in the order that we mentioned. Look for the power rule first, product rule second, quotient rule third, and in the end make sure not to leave any negative exponents. Pause it, see how you do, and check back in a minute. Looks like we need all of our rules for number 1. We have the power rule first, multiply to get 20. Product rule next, add 20 and 1 to get 21. And quotient rule last, 21 minus 10 to make m to the 11th. On number 2, we don't need the power rule, but we do have a product in the bottom. So keep the p and add negative 5 and negative 2 to make negative 7. And then we have a quotient, so let's subtract the top exponent minus the bottom exponent, which gives us a double negative. And 3 and 7 add up to 10, p to the 10th. On number 3, we do need the power rule, so let's multiply 4 and 2 to make 8 to get started. And then we have a quotient, so subtract the exponents, which makes a negative 4. We don't want to leave that negative, so we change it to a fraction, 1 over y to the 4th. Lastly, no power rule this time, so start with the product. 2 plus 5 makes 7. And then the quotient, 7 minus negative 3 gives us a double negative, and x to the 10th. The last topic in this section is scientific notation because it uses exponents. How about for starters, try putting 0.1 to the 13th power on your calculator. With or without the parentheses, doesn't matter too much. We just would like to see what happens. On this calculator here, it writes the result as 1 times 10 to the negative 13th. What we see here is an example of scientific notation. Sometimes the calculators don't put the times 10, they might put 1e negative 13. The e takes the place of the times 10. The 1 is the same, the negative 13 is the exponent. What the calculator is trying to do is take a long number and squeeze it down so it'll fit on the screen. See an example here of a number in scientific notation? The idea is that the decimal is not really where we see it here, but actually 4 places to the right. I know that it's to the right because that 4 is positive, whereas when the exponent is negative, it would be to the left. So the calculator is giving us a scientific notation answer here, and it means the decimal is not really here, but it's actually 13 places to the left. So we're talking about 0.0 6, 7, 8, 9, 10, 11, 12. All of those zeros before the 1. That would be too long a number to fit on the screen, so it's been condensed into scientific notation. So let's try it out with this. Let's take this number in scientific notation and try to write it in standard form, like a regular old number. So the decimal is not really here. It's actually 4 places to the right. Let's think about shifting it over 1, 2, 3, 4 places. When you go across the 0, that counts as 1. Go across the 3, that's the second. 2, 3, and it makes an empty space which we'll fill in with a 0. So let's take that 2.032. Let's move the decimal 1, 2, 3, 4 places to the right and fill in with a 0. So it looks like it's actually 20,320. When the exponent on the 10 is positive, it's going to make a big number like 20,320. On the other hand, when the exponent on the 10 is negative, because the decimal gets moved to the left, it's going to make a tiny number like 0.000 something. So let's see, if we were to move that decimal across the 8, that would count as 1 place. We want to go a total of 7 places, so we need to go 1 and then 6 more. In other words, we're going to fill in 6 zeros in front of that 8, 6, 9, 3. So let's double check. 1, 2, 3, 4, 5, 6. This looks good. The decimal was here originally, and when I move it 7 places to the left, 1, 2, 3, 4, 5, 6, 7, it ends up way over here, and all of those new spaces get filled in with zeros. So we can see what I mentioned a second ago. A negative exponent on the 10 makes a tiny number, 0.000008693. We'd like to also be able to go the other direction, take a long number and put it into scientific notation. I can see that this long number is a big number, so I'm expecting a positive exponent. Part of the trick is knowing where to put the decimal when we write it in scientific notation. And the idea is when we're done, we'd like that original or first number there in the front to be somewhere between 1 and 10. So think about where you could put the decimal in this 93000 to make this a number somewhere between 0 and 10. 1 and 10. For instance, if I put the decimal here, 0.93 would not be quite big enough. I want it bigger than 1 but smaller than 10. So what if I put it between the 9 and the 3? 9.3, that would be between 0 and 10. That has possibilities. Or what if I put it over here? I'd get 93, and that would be too big. So we do want it between the 9 and the 3. 9.3 times 10 to the something. So if we're thinking about putting the decimal here in scientific notation, let's see how many spaces would we need to tell somebody to move it to get all the way to there. So it looks like it'd go 1, 2, 3, 4, 5, 6, 7, 8, 9 spaces to the right. That means we would call it 9.3 times 10 to the 9th, positive 9, to make that big number. Next up, if we want to make sure that this first number we write down is somewhere between 1 and 10, let's see where the decimal should go. If I put it to the left of the 1, that'd make it too small. To the right of the 1 looks good. To the right of the 6 would be too big. So we better put it in between the 1 and the 6. And to let folks know that they would then move it over to make this tiny number. Since it's a tiny number, remember we're expecting a negative exponent. The decimal between the 1 and the 6 would need to move 1, 2, 3, 4, 5, 6 places to the left to give us this 0.0000167. By the way, when you're putting answers like this into MyMathLab, be sure to use the multiplication symbol from the mouth palette and not the letter X, because this is a times, not the letter X. Multiplication symbol. try pausing the video again and practice moving the decimal around, seeing what these numbers would look like in standard form or in scientific notation, depending what is blank. So if we move that first decimal 5 places to the left, we'll end up with 4 zeros in front of that 3. To turn 78,000 into scientific notation, we want the decimal between the 7 and the 8. And then it would need to have an exponent of 4 to bring it back to 78,000. Answer 7 would be 2032.1. And answer 8 would be 1.94 times 10 to the negative 5th.